climate change. I'm excited to welcome tonight's speaker, the MIT Assistant Professor and the Silverman Family Career Development Professor, Dr. Priya Donti. Dr. Donti's nomination for this lecture was spearheaded by a group of faculty on the board of the UW Program on Climate Change. The Program on Climate Change, or PCC, aims to bring together researchers and students working on climate science across campus to facilitate interaction, ignite interdisciplinary research, and strengthen interdisciplinary education. Dr. Donti's nomination was coordinated through the PCC and involved an interdisciplinary group spearheaded by the Evans School of Public Policy and Governance, with the Paul G. Allen School of Computer Science and Engineering, the Department of Atmospheric and Climate Science, and the iSchool. I would like to thank those units, as well as the Graduate School, for sponsoring this lecture. I'd also like to thank you, the audience, for coming, including those watching on live stream. So there's a few housekeeping items before we get started. Please silence all cell phones. No personal video or audio recordings are allowed. This evening talk is both live streamed and recorded on the Office of Public Lectures YouTube page. Please no photos whilst the speaker is on stage, with the exception of our student assistant. Questions can be sent in on Slido using the QR code in the link on your registration reminder. You can also like other audience members' questions. And for those who would like to ask questions verbally, please come up to the microphone and remember to ask questions in the form of a question. Thank you for your cooperation. So Dr. Priya Donti will be introduced by the UW's Weyerhaeuser Endowed Professor in Environmental Policy and the Daniel J. Evans School of Public Policy and Governance, Professor Ann Bostrom. As Anne makes her way to the stage, I invite you to please take a moment to introduce yourself to the people seated around you.
Good evening. Thank you all, and thank you, Becky. I'm Ann Bostrom. I have the honor and pleasure of introducing tonight's guest. Dr. Priya Donti is an assistant professor and the Silverman Family Career Development Professor at MIT in the Department of Electrical Engineering and Computer Science and the Laboratory for Information and Decision Systems. Her research focuses on machine learning for forecasting, optimization, and control in high renewables power grids. Methodologically, this entails exploring ways to incorporate relevant physics, hard constraints, and decision-making procedures into deep learning workflows. Dr. Donti is also the co-founder and chair of Climate Change AI, a global nonprofit initiative to catalyze impactful work at the intersection of climate change and machine learning. Professor Donti received her PhD in computer science and public policy from Carnegie Mellon University and is a recipient of the MIT Technology Review's 2021 35 Innovators Under 35 Award, the AI 2050 Early Career Fellowship, the Association for Computing Machinery SIG Energy Doctoral Dissertation Award, the Siebel Scholarship, and the U.S. Department of Energy Computational Science Graduate Fellowship, as well as a number of Best Paper Awards, including, for example, the ICML, or International Conference on Machine Learning Association, the Association for Computing Machinery International Conference on Future and Sustainable Energy Systems, the Power and Energy Conference at Illinois, and the Conference and Workshop on Neural Information Processing Systems, or NeurIPS, workshop on AI for social good. So please join me in welcoming to the stage Dr. Priya Donti.
Awesome. Well, thank you, Anne and Becky, for those really kind introductions, and to kind of everybody who came together to host me here. Thanks so much. So today I want to talk about climate change. So climate change is one of the most pressing issues that we as a society are facing today, and we're already feeling its effects, from storms to droughts, to fires, flooding, ecosystem degradation, expansion of the range of certain diseases. These impacts are being felt globally, and they're disproportionately being felt by the world's most disadvantaged populations, which creates a huge imperative to act quickly on this issue. In particular, acting on climate change has two kind of big axes of action associated with it. The first is climate change mitigation, so reducing or preventing greenhouse gas emissions that are in the atmosphere and driving global warming and climate change. According to the UN Intergovernmental Panel on Climate Change, for instance, one target that kind of looms large is hitting net zero emissions by 2050. And this requires a rapid transformation of virtually every sector of society, from energy to transportation to agriculture and so forth. In addition, given that we unfortunately will face some of the impacts of climate change, and we already are experiencing them, it's also important that we kind of take large-scale efforts to adapt to climate change, to kind of build robustness and resilience to the effects of a changing climate. And this requires large-scale efforts at a global scale, but efforts that look differently depending on the details of what will happen at a particular locality. And so given this need to act really rapidly on climate change and to kind of understand where we are in actually making progress on the issue, one question that might loom large is, lots of people are talking about artificial intelligence. How does artificial intelligence fit into all of this? And the answer, as with many things, is complicated. So there often in the media, you'll hear kind of one of two ways that AI is affecting climate change. The first is AI is going to save us all. AI is going to help us address climate change. It's going to be a solution to every single problem we have in climate change. While I don't ascribe to that particular view, there are places where AI indeed can be useful in climate action, and I'll talk through those in a bit. The other story you'll hear is AI is causing us to, build lots of data centers. It's consuming tons of energy, and AI is, as a result, going to be the cause of a huge climate catastrophe. AI indeed has kind of, very large computational and hardware impacts, and this is also something I'm going to talk about, though again, there's some nuance to that story. And this is the picture that you will often see kind of depicted in media. AI is good because it can be used for climate action, and AI is bad because it has its own direct impacts on the environment. That's not the whole story, though. In particular, AI is used also in many ways that have implications for climate change that are not necessarily so great. So in the same way AI is used to accelerate some of our climate-related strategies, it's also used in ways that are actively counterproductive to some of our climate change-related strategies to basically increase the effectiveness of emissions-intensive industries. AI is also creating various societal level shifts in changing sort of how we consume goods and information, changing our transportation systems, changing kind of who holds power and agency in society in ways that have huge implications for climate action, but are also often not talked about. And so what I want to kind of spend my time with you today doing is actually talking through each of these different phenomena in order to kind of round out the picture of when we talk about AI and climate change, what does that actually mean? What are the various different ways in which AI and climate change interact? And then kind of close by talking about what can we actually do to align the use of AI with climate action, make sure it's an asset as opposed to kind of deterring from our efforts to address climate change. But before I dive in, I know that we have kind of an audience coming from many different backgrounds, and so I do want to spend a little bit of time talking about, what I actually mean when I say AI. So AI refers to any computational algorithm that allows a machine to do something complicated. And I realize that's not a particularly precise definition. There are lots of definitions out there which have, many kind of layers of disagreement in terms of whether it's the most precise definition. But at a kind of first order level, you can think of it as an algorithm that allows a machine to do something complicated. Often these are tasks associated with human intelligence, things like speech or reasoning or perception, but not always. For example, artificial intelligence is used to do things like forecast renewable energy on the power grid, which is something that I don't know, I'm not smart enough to do that. But so there are various different kinds of tasks that AI can be doing. There are two major categories, actually, when we talk about AI. The first is rule-based systems. And these are techniques that, in situations where we know the rules, for example, the game of chess, we know what the rules are, but where the hard thing is figuring out how to act in the face of those rules in order to do something smart. Rule-based systems basically figure out a way to reason over those rules to, for example, figure out how to play a good game of chess. The other kind of branch of AI, and the one that is sort of often in the news today, is machine learning. And machine learning is used in situations when it's actually really hard to write down a set of rules. So the image on the slide is showing, for example, a picture of a banana. If I look at a picture of a banana, I can tell you it's a banana. But if you ask me to write down a precise set of rules that described exactly why I think it's a banana and why it couldn't be anything other than a banana, that would actually be a really difficult thing to do. And so machine learning is used in situations where it's easy to give examples, but it's hard to write down rules. And you give a machine learning algorithm a bunch of examples, often in the form of data, and it learns patterns in that data, implicitly figuring out the rules in order to then apply those rules. So in order to, for example, then figure out, given a new image, is it a banana or not? Within machine learning, there are kind of three major categories of this kind of broader idea of get a bunch of examples, get a bunch of data, and extract patterns from them. The first is called supervised learning, and this refers to techniques where you have a data set that has some set of labels on it, some set of answers. So for example, a bunch of images that are labeled, is this a banana or not? And your machine learning algorithm tries to learn the relationship between your data and the labels on it. So learn the relationship, for example, between the pixels in an image and the label of banana or not. Another category is called supervised learning, and unsupervised learning. And this is used in situations where you have a data set that maybe doesn't have labels or answers on it, but where you're trying to still figure out some pattern in it. Clustering is a really common example of unsupervised learning. Basically, if I have a bunch of images and I want to understand which ones are similar to each other, I might run a clustering algorithm to figure out which are similar to each other. And afterwards, I might look at those clusters and say, okay, some of these are, this cluster is bananas, this cluster is dogs, this cluster is cats. But basically, I haven't given that information to the algorithm ahead of time. It's just figuring out structure in the data. A lot of our kind of favorite generative AI techniques, so things like ChatGPT, are also a form of unsupervised learning. What they're doing is that they're basically taking in a bunch of text information from the internet, learning some structure or pattern regarding what it means to look like text, and then spitting out outputs that also look like text, basically leveraging that pattern of what text is and kind of spitting that out. And so there's no kind of ground truth or answers being provided in that context. It's in some sense just pattern matching on kind of an unlabeled data set. And a third big category of machine learning is called reinforcement learning. So this is used in situations where you don't actually have a fixed data set ahead of time, but what you're trying to do is learn how to take actions in order to change some quote-unquote environment. So for example, a battery that I might want to charge or discharge as it's connected to a power grid, or a player in a game which is going to interact with an online gaming environment and get back some feedback about how well it's doing. And what reinforcement learning algorithms do is they basically try to take some action. So for example, a player in a game is going to try to take some action. then based on what happens, that player gets a reward signal that was either good or bad, and how good and how bad was it. And then the player basically adjusts how it chooses to take actions based on the feedback it's getting. So this one concept of machine learning, kind of learn patterns in data, basically crops up in many different ways. And you'll kind of see some of these themes pop up when I talk through different ways that AI can be used for climate action. There are a couple of other kind of terms I wanted to bring up just because I feel like they're often popping around in the media and it might be helpful to understand what they are. So sometimes when people talk about machine learning, they're kind of describing what the type of model is. What is the kind of thing that I'm using to actually learn the patterns in the data? You'll often, for example, hear about neural networks or deep learning or transformers or large language models or foundation models. These are all terms that refer to a particular type of machine learning model, which basically involves taking a bunch of small functions and stringing them together so you get one big powerful function. And there are lots of other types of models, support vector machines, decision trees. Basically, neural networks are not the only type of machine learning, even though you kind of hear about that quite often. You also hear about terminologies that reflect not the model you're using, but the type of data you're learning about. So terminologies like computer vision mean you're processing images and videos. Natural language processing means you're processing text. Robotics means you're working on kind of physical, mechanical equipment that moves, and so forth. And one thing I'll kind of mention for those who are curious, you'll hear often the term large language models. This is kind of not a great terminology in that large language models are a type of neural network, but they can also be used to process images, not just language. So just something to kind of bear in mind when people are using the terminology. And then there are various ways that these models are used, kind of combining or kind of reflecting different requirements that we have for the use of these models. So for example, when we talk about physics-informed machine learning, it means that we care about the fact that the outputs are actually sensical with respect to certain physical properties. So if you're using machine learning to predict climate phenomena, that you want the climate properties and the physical properties to make sense. And so physics-informed machine learning refers to places where you're kind of combining physics and data-driven techniques. You often have situations where you want interpretable machine learning, where you can understand what's going on under the hood, where you can understand uncertainty quantification, where you know how confident the model is or not, and meta and transfer learning, which basically refers to situations where you kind of create a model in one context with one set of data, and you want to see if you can actually, if it works when applied to a different set of data. So I wanted to go through this, not that every kind of piece of this is necessarily critical for the rest of the talk, but I know that kind of terminology around AI and machine learning gets thrown around quite a lot in a way often that is meant to be obfuscating and scary and exclusionary. And I think it's really important that actually we're all kind of educated on some of these terminologies so that we can actually engage in conversations about what it means to then shape the use of AI for climate and for other societal applications. Okay, so often AI and machine learning are kind of bandied as these, cure-all, they're gonna work for everything, for everyone, and save everything. But fundamentally, AI and machine learning are just tools that have their strengths and limitations. So for example, machine learning is good at learning patterns in data and then using those patterns from the data. It's good at performing tasks at scale. If you asked me, again, kind of, does a particular image have a dog or a cat in it? I could tell you that. If you asked me to do that for 1 million images, I probably wouldn't want to spend my time doing that. And so machine learning is good at kind of automating these tasks at a much larger scale than humans might be wanting to perform them at. Similarly, it can be good at optimizing complex systems, things like heating and cooling systems in buildings, where you're taking in tons of information from a bunch of different sensors and figuring out what to do. It can be always on in a way that kind of individual humans can't necessarily be. It can be good at combining many different kinds of inputs like images and outputs of weather models and text, and combining them and finding powerful relationships between them. And it can also be integrated with other methods like kind of climate models and physical models and so forth. So there are a lot of things to be excited about when it comes to AI and machine learning. But there are also a lot of limitations. Machine learning is a tool. It's not the right fit for every task. If your task doesn't look like, for example, learning patterns in data or learning patterns in large amounts of data, it may not be the right tool. Machine learning can also be overconfidently incorrect. So it'd give you an answer that is wrong and be so certain that the answer is correct. And many of you who may have used ChatGPT or other, kind of tools may have experienced this firsthand. Many techniques to make data are compute hungry. Not every machine learning technique is, but some machine learning techniques, and in particular some of the cutting edge ones that are often used by kind of large tech companies, will require a lot of data to train, they'll require a lot of compute to train, and this of course has kind of environmental and other impacts that are really worth thinking about. Machine learning techniques also rely on the data that they're given being of good quality. If you're learning patterns in data and your input data is garbage, then the patterns you're learning are probably garbage as well. And so this is usually kind of framed as this phrase, garbage in, garbage out. Machine learning techniques are also not objective. They're extremely biased. For example, if the data I give my machine learning model is encoding histories of redlining in housing where people were discriminated against in terms of which housing they could get, and I try to use that data to predict which houses are probably best suited for energy efficiency retrofits, the fact that certain housing was more underinvested in relative to other housing is going to show up in my data, and it's going to bias what I actually predict in terms of this house is a slam dunk in terms of energy efficiency retrofits. We're only going to predict things that we're already well invested in and where there's very little risk. Similarly, the way that we design machine learning models encode some of our own biases as we design the methods and maybe bake in our own assumptions. And the settings in which we choose to use machine learning also come with various biases. For example, it's really valid to ask questions like, why is machine learning more often used to predict crime on kind of marginalized populations as opposed to predicting white-collar crime in the financial sector? So there are lots of kind of biases and choices that we're making when we're actually deciding where to use machine learning. And then kind of one subtle point is that machine learning assumes that the data you give it is the whole world. So if the world actually looks different than that data, then it's not going to be able to deal with that. For example, there were a lot of machine learning models used to predict electricity demand before the COVID-19 pandemic. And when the COVID-19 pandemic happened, how we used electricity fundamentally shifted because we were, at home rather than at work, and that completely changed our electricity demand patterns. And machine learning models that thought the whole world was pre-COVID electricity usage were not able to deal with a different world where we were looking at during COVID electricity usage. And so machine learning models assume that the information that are given are encoding all of the rules they need to know. And if those patterns aren't persistent, if those patterns change, then the machine learning model doesn't continue to be valid in that setting. All right. So that's my little tutorial on AI and machine learning, but I want to get back to kind of the main thrust of the talk here, which is what do all of these things mean for climate change? And so as I motivated at the beginning of the talk, there are kind of four main ways that I would say AI and climate change relate, and I want to kind of go through each of them in a little bit of detail. So the first is, how can AI be leveraged for climate action? So several years ago, a group of collaborators and I, coming from AI and climate change related areas, got together and asked ourselves this question: where is it that AI can be useful for climate action? And we examined this question across many different sectors that were critical for climate action, like our energy systems, our transportation systems, our agricultural systems, and so forth. And while I'm not going to be able to go through literally every single application we uncovered, for those who are interested, I encourage you to check out this paper, Tackling Climate Change with Machine Learning. I do want to talk through some common themes that came up across the examples we looked at in order to maybe help build a mental model of the kinds of ways that AI and machine learning can play a role. And by the way, having given this whole tutorial on AI and machine learning, I will use these terms interchangeably, given that machine learning tends to be kind of the bigger pot of techniques that are used within AI. So if I'm sloppy about that, apologies, but I'm going to use them interchangeably. All right, so Where are some ways that AI and machine learning can be used for climate action? A first big theme that comes up is distilling raw data, like satellite imagery, into actionable information that we can use for climate action. For example, there is a global coalition of nonprofits called Climate Trace, which is taking satellite imagery and on-the-ground data, learning patterns in that using machine learning, and using that to understand at the kind of specific entity level, so at the level of a specific kind of industrial facility or building, what the greenhouse gas emissions are that are being emitted by that entity. And that's being used to create independent greenhouse gas inventories that can be taken to the UN climate change negotiation processes, and that can be used to actually build the basis for climate policy around how we actually reduce those greenhouse gas emissions. Similarly, there are various initiatives that are basically taking satellite imagery, learning patterns in it, and using it to pinpoint where deforestation might be happening, or the energy efficiency characteristics of different buildings around the world, or identifying the types and yields of different crops on agricultural land in order to help us understand what's going on and how we need to maybe adjust our agricultural practices to be resilient to climate change impacts. All of these applications are basically giving us proxies for the true information. So in some sense, the best thing we could do is actually do large-scale on-the-ground surveying to figure out, okay, what are the emissions coming from this building? Or to do large-scale on-the-ground surveying to understand what are the crops on this piece of agricultural land. But unfortunately, that's not always feasible from a kind of personnel capacity perspective, from a funding perspective. And so these kinds of techniques, kind of learning information from satellite imagery, can help us fill in the gaps in situations where that information could be really relevant to make decisions, but where it is hard to get on the ground. Another common theme that comes up is improving predictions. For example, the image on the slide is from a nonprofit called Open Climate Fix. They work with the UK power system operator in order to improve their predictions of electricity demand and of solar and wind power production. These kinds of predictions are really important for managing power grids with large amounts of renewables, and I'll kind of get to this in a little bit as well. And so what they do, for example, for their solar power predictions, is they use machine learning to combine a number of different sources of information. So they will combine, for example, historical data on how much solar power was produced, weather forecasts that come from physical weather models, numerical weather prediction models, and even overhead imagery showing how the clouds are moving and as a result how they may shade solar panels. And they're able to combine all of this information within a machine learning model and use that to learn really strong relationships between this data in a way that allows them to come up with really good solar power forecasts. And they were able to, by doing this, actually cut the error of the forecasts that were being used in half compared to what was being used before. And this concept of kind of creating good near-term predictions comes up also when predicting things like demand for public transportation in order to help kind of schedule public transportation or bikes better, as well as prediction of extreme events. So while these two themes both have to do with, in some sense, I need to kind of provide information to somebody who's going to make a decision, there are also places where machine learning is used to actually help with automated decision making. So for example, the heating and cooling systems in our buildings are extremely inefficient, and there are kind of ways that they can be operated that might improve their efficiency by something like 30%. And the way you do this is you take in a bunch of information from sensors about things like what the temperature of your building is it occupied right now? What's the weather outside? What are the characteristics of your building? And basically you can combine all that information, again, learn patterns in it, and use that to come up with more kind of clever control strategies for the heating and cooling system in your building. This is often done using reinforcement learning. Remember the thing I talked about where you have an algorithm that's interacting with some kind of environment, like the building and figuring out what actions to take. And this kind of idea of use reinforcement learning to control something like a heating and cooling system comes up in a lot of places, actually controlling the cooling systems in data centers, controlling different power generators on power grids, and even actually helping us resolve freight auctions in transportation systems, which are used to actually allocate how kind of different goods are shipped and by whom they're shipped. Similarly, there's a kind of whole area of work called predictive maintenance, which basically tries to understand on critical infrastructure where there might be kind of inefficiencies, either kind of predict that ahead of time or in real time, so we can fix those inefficiencies. The image on the slide is from the German rail operator, Deutsche Bahn, which basically uses machine learning to identify places in which the switches on the railway infrastructure might be breaking in order to actually fix those as quickly as possible and keep the trains running on time. For anybody who has a connection to Germany or Europe, you might say, Priya, the trains in Germany are not actually that punctual. Well, it might be even worse without AI. Another big example that comes up here is kind of detection of methane leaks. So when natural gas is extracted, it's then transported to where it's used for heating or electricity along lines and around pipelines and compressor stations. And natural gas can leak out as methane into the atmosphere along that pipeline. And methane is a really potent greenhouse gas that we really don't want leaking into the atmosphere. And so machine learning has been used to actually try to detect where are leaks already occurring, or where is a leak likely to occur because we see something wrong in how the natural gas is flowing through the pipeline, in order to try to fix that either in real time or ahead of time. So both of the prior examples had to do in some sense with optimizing a real world system that is already kind of in operation today. Machine learning is also used to help accelerate the process of scientific discovery. So help us to, for example, learn from the past attempts that we had to synthesize a battery and use that to recommend which battery we should try synthesizing next in order to reduce the number of design cycles it takes to create that better battery. And this can be really important. Kind of synthesizing and testing a battery can be a process that takes many months to years, which means that kind of every single battery you try, you kind of want to make sure you're making progress towards getting to that next better battery. So machine learning can be used to basically make recommendations about what to try next. Similarly, machine learning can help us to approximate time-intensive simulations. So the image on the slide is from a paper in 2019, which basically used AI to approximate cloud physics. So basically take a model of a cloud and learn like a cheap approximation to the physics of that cloud, so that that cheap approximation could be stuck into a bigger climate model. Climate models are really expensive to run, so if you can make parts of them cheaper, you can basically make it easier to run the overall climate model. And that basically means being able to run more scenarios to figure out what's going to happen. That means figuring out ways to get more granular insights. So instead of understanding what happens at the resolution of the entire state of Washington, you can figure out what actually happens in Seattle, so we can come up with more targeted disaster response strategies to actually figure out what to do in Seattle. And since then, while kind of in 2019, a lot of the initial work was approximate parts of climate models. A lot of the work has progressed to actually allow even approximations of bigger parts of climate and weather models. And some people are even looking at, can you use machine learning to replace an entire climate model end to end? In all of those cases, there's usually some form of combining data and combining physics, so it's not literally just a naive machine learning model, but the techniques here have definitely gotten a lot more powerful to allow us to approximate climate models, or similarly energy models or city planning models. Last but not least, while I've motivated that machine learning kind of requires data in order to learn patterns, there are also ways that machine learning can actually help us with the management of data for other purposes. For example, the US national government puts out different data sets on energy generators, where one data set might report the amount of power produced by a generator, another might report the emissions associated with those generators. But where the same power generator in two different data sets might not be referred to with the same ID or the same name. And so it's really hard to merge these data sets at scale in order to actually understand what's going on. So one entity has been using machine learning, one entity called the Catalyst Cooperative, a cooperative in Colorado, they've been using machine learning to actually try to automatically detect which rows in different data sets might correspond to information about the same power generator in order to actually automatically help to merge some of these data sets and allow them to be used for policy analysis, for advocacy, and so forth. Another example relating to the image on the slide is about kind of creating future scenarios relating to how much wind power production we might have. So when you're kind of trying to plan out what a future energy system should look like, where you should build things, you often create different scenarios to figure out what are the different ways that electricity demand could look in the future, what are the different ways wind production could look in the future, and that gives you information to figure out how to plan out your renewable energy system. And so what this group did, coming out of the University of Washington, is they learned, they had a past data set of wind power production. They used a machine learning model to learn patterns in that, just to figure out what does it mean to look like a time series of wind power production. And then they basically said, well, in the future, we expect that the wind power production might look more extreme in one way or the other. So they kind of adjusted a little bit what the machine learning model learned. And then they used that to generate a bunch of different scenarios of what wind power production might look like in the future. And that can basically help to plan out future energy systems in a more useful way. So again, these are kind of, not necessarily exhaustive, but I think they provide a reasonable picture of some of the more impactful ways that AI and machine learning are being used for climate action. And one thing to note in the examples I gave is that most of the types of machine learning that I kind of talked about there are not foundation models or large language models or kind of the type of AI that is often pushed right now as kind of the AI to use. And in particular, these different kinds of settings kind of require a really diverse set of approaches. Today, often in the main discourse on AI and machine learning, you'll hear about methods that require big data, that require large amounts of compute, that say data gives us everything you need. If we had knowledge about a particular system before, we don't need it, we can throw it away, and that have a specific notion of what performance means, some notion of average accuracy across all of your data points. And in reality, and when we think about climate change related settings, there are a lot of differences on the ground. Sometimes we have less data, or sometimes we have a lot of data, for example, on power grids, but it's collected in different places, and it's really hard to actually centralize it somewhere because you actually have to then communicate it from one place to another. And sometimes so as a result, you can't always assume that you have kind of one big pocket of data to learn from. Sometimes you don't have as much compute. Sometimes you're trying to run something on a smartphone or on a small sensor on a power grid. And of course, we really want to reduce the energy and emissions associated with these methods because of the environmental impacts associated with that. Sometimes you have useful knowledge about a particular task or a particular domain that you don't want to throw out. So on a power grid, we know how the physics of the power grid work. It would be kind of wasteful to throw that out and relearn it all from data, because we already know it. We don't need as much data where we need to relearn it. And so sometimes there are approaches where it is useful to bring in knowledge you already have. And there are a diverse set of metrics that we might use to actually evaluate the quality of a machine learning model. We might care more about whether it is safe than whether it's perfectly accurate, or if it's interpretable, or if it preserves privacy. And so the types of metrics that we actually care about across different settings are different. And what this means is that even though there's, again, this predominant paradigm that there's a specific type of AI, a specific set of techniques that we want to use and that are going to be impactful for climate change, like generative AI is going to be impactful for climate change, and as a result, we should keep funding a bunch of data centers being built and that specific type of model being deployed. In reality, there's a really diverse set of techniques that we should be kind of fostering that are kind of being developed by a diverse set of organizations from across academia, nonprofits, different types of industry, and so forth. And so it's really important to challenge some of these narratives of we should build a specific type of AI to address climate change. So for example, my own work looks at, in the context of the electric power sector, ways that we can bridge between traditional electrical engineering and machine learning in order to actually make sure that we have safety guarantees that come from optimization and control in electrical engineering and that come from machine learning. And what we basically do is we look at specific sets of machine learning models, particularly deep neural networks, and we figure out ways to basically incorporate physics, hard constraints, electrical engineering constraints from power grids into the way we design those machine learning models in the first place. And as a result, you get models that kind of are physically robust, are safe, and so forth. And we use that for a variety of things like predicting electricity demand on the power grid in a way that makes sense from the perspective of how power grids are scheduled, or we use it to basically approximate optimization algorithms on the power grid. I'm speeding through that part because I realize I'm very much blowing through my time, but I'm happy to kind of dive in deeper if there are any questions about this. But the key point is that the way you actually develop machine learning methods looks fundamentally different depending on the setting you're developing it in. And as a result, we really need to be fostering a diversity of approaches coming from a diversity of organizations if we actually want AI and machine learning that serve the needs of climate change related applications. Okay, so having talked about how AI can be used to address climate action, I do want to talk a bit about the impacts of AI's direct impacts from its computation and its hardware. So when we talk about the impacts of AI and machine learning, there are two types of impacts that it's actually important to keep in mind. One category is called operational impacts, and these are the impacts that come when you're actually running a machine learning model, when you're actually training it or using it. And these impacts come from the electricity consumed when you're actually running computations, as well as, for example, water used to cool data centers during that time. The other set of impact is called embodied impacts. And these are impacts that are associated, for example, with the hardware on which computations are run. And there are emissions that are associated with actually producing and transporting that hardware. There are materials impacts from kind of the construction of the hardware. There are kind of impacts from the disposal of hardware. And both of these impacts, both in some sense the software side and the underlying hardware side, are important to take into account. In 2020, we had some estimates of kind of what is the percentage of greenhouse gas emissions that are coming from, machine learning. So in 2020, the overall information and communication technology sector, so covering not just AI, but kind of, internet, kind of communications, all of that kind of stuff, made up about 1.4% of global greenhouse gas emissions. And some unknown but small fraction of that was coming from AI. Now, those numbers are changing, and I'm going to talk about that in a moment. But this kind of estimate of kind of at a global scale, what are the greenhouse gas emissions, it's called a top-down estimate. There's also a lot of work trying to do bottom-up estimates, which ask questions like, for a specific AI model or a specific AI workflow, what are the impacts associated with that? And what these will look at is the kind of impacts of machine learning across three different phases. The development phase, in which you're trying to figure out what the structure of your machine learning model should look like. The training phase, where you've settled on your structure and then you're now using that model to learn patterns in data. And then the inference phase, where you've created your model and you're actually using it, you're actually applying it to make some kind of prediction. Each of these phases has different kind of amounts of emissions associated with each time you do it. So the development phase has a lot of emissions associated with it because you're trying out a bunch of different structures, but you do that very few times. The training phase has kind of a medium amount of emissions associated with it, and you do it a medium amount of times. And the inference phase, once you have a model and you use it, each inference takes a smaller amount of emissions, but you do it a lot. You kind of train a machine learning model so that you can use it to answer a lot of questions or to analyze a lot of satellite imagery. And so basically there are actually questions about, you have these processes that are very emissions intensive, but you do very few times, and these other processes that are not very emissions intensive, but you do a lot. What are the total emissions associated with each of these phases, and what does that mean for our actual actions we take in order to reduce those emissions? So bottom-up estimates are useful for asking those kinds of questions. Now, the numbers I gave for the total emissions, 1.4% for ICT and AI is some small fraction of that. We don't know what the numbers look like today, but they are changing. And the reason that they're changing is because the types of models that we're increasingly using are changing. In particular, different models have different impacts associated with them. There are some machine learning models that I can easily run on a laptop in order to get answers. There are others that have to run on huge data centers. And the emissions associated with each of those different types of models is really different. So one thing I want to emphasize is there's actually nothing inevitable about machine learning needing to use a lot of energy. We can choose to create and use more efficient models in order to reduce impacts. And yeah, I mean, I think as the kind of models we're using are becoming larger and larger and those models are being used more, there is something to be concerned about. Electricity demand is rapidly growing, and between 2019 or 2021 and 2026, kind of, backwards and projected forward. If you look at the global electricity demand from data centers, AI, and cryptocurrencies, so a bunch of technologies bundled together, but nonetheless the set of technologies, you see a kind of 2 times increase in the global electricity demand between 2021 and 2026. And to emphasize just how different this is from where we were before, if you look at the increase in electricity demand from these kinds of technologies between 2010 and 2018, kind of a similar length time period in the past, the increase was only 6%. And this was despite the fact that we were actually increasing in that period between 2010 and 2018, we increased the amount of compute we were doing by 6 times. So what was happening is we were using a lot more compute, but hardware was getting efficient at a pace that matched that. And right now we're starting to enter a realm where we're using even more compute, but hardware is not necessarily getting efficient at a pace that's curbing that. And so we're in a really different realm, which means we have to really ask ourselves what to do about this emissions problem with kind of the largest AI models that are being used today. And there's some kind of subtle dynamics and trends that are going on here as well. So Facebook did a study on kind of what are the emissions implications of training models versus using models, given again that training is more energy consumptive but done less frequently, and using models is less consumptive but is done more frequently. And what they found is that for their earlier models, the kind of total emissions associated with training versus usage was about 50-50. Whereas for some of the newer language models that they're using, the kind of training is actually not taking as much total emissions as the usage of the models. And part of what's driving this is that, and again, I'm throwing some figures up very quickly, but part of what's driving this is that before, when we were using quote unquote task-specific models that were more tailored to a particular task, versus when we're now using general purpose models that are meant to kind of be usable across many tasks, each use of a general purpose model is more energy consumptive than each use of a task-specific model. And it means that kind of per use, multi-purpose model can be like 10, 100, 1,000 times more expensive than a task-specific model. And so it means that our inference phase, our use phase, is actually growing in its share of emissions relative to the training phase. And this is important to know because it implies different levers about what we do in order to bring that consumption down. So one common argument I get when talking about the energy use of AI models is, okay, but why don't we just put a bunch of renewable energy on the grid and aren't we done, right? Then your energy use is carbon free, great. And that is really important, but it is insufficient. A lot of the pathways for how we actually decarbonize the energy sector rely on us actually improving the efficiency of the sector and actually reducing the amount of energy that we're using. And so if we have this kind of growing electricity usage from AI, that conflicts with the fact that actually all of our strategies to decarbonize the energy sector rely on kind of making usage more efficient. So efficiency is really important. And then, as we talked about earlier, electricity usage is not the only type of impact that these methods have. Kind of cooling data centers draws water, and often in water-stressed regions that competes with other uses for that water. And also, kind of, there are huge minerals and materiality impacts that come with hardware and computing infrastructure, often in kind of, war-torn regions, then a huge human labor implications, and that we really need to care about. So having taken that tour through the kind of impacts from AI computation and hardware, as I mentioned earlier, there are kind of some additional pieces to this picture that I want to try to flesh out in the last few minutes. So the next piece here is ways that AI is used to increase greenhouse gas emissions. A kind of common example here is that AI is actually pretty widely used to accelerate oil and gas exploration and extraction. And some reports have estimated that AI and machine learning have boosted production levels of oil and gas, in some cases by as much as 5%, and has generated potentially hundreds of billions of dollars in revenue for the oil and gas industry. And the challenge here is that basically AI is helping to make oil and gas technologies kind of cheaper and more competitive relative to what would replace them, and this slows the transition to kind of cleaner alternative sources. In addition, AI is also used in agriculture for things like the Internet of Cows, which are used to basically coordinate bovine agriculture to make it more efficient, and kind of, bovine agriculture is a big contributor of methane emissions. So this is arguably also not having a great climate impact. Potentially less obvious than those applications, though, are ways that AI is completely shifting various societal kind of applications and how we relate to each other. In ways that actually have huge implications for climate, even if we don't always think of them as climate applications. For example, AI and machine learning are often used to try to further autonomous vehicle technologies. And there have been a lot of studies showing that the effect of autonomous vehicles on climate may be positive, it may be negative, we're not sure. And this is because, for example, using AI to help drive a vehicle might actually make the driving itself more efficient, but it might cause us to actually drive more miles because it becomes cheaper to drive a particular mile or easier to drive a particular mile. That's called a rebound effect. And by making kind of private transportation more attractive, it might do what's called locking us into our current mode of private transportation rather than facilitating us moving away from that and towards more public and multimodal transportation. Now, we don't have to take this for granted. There are various ways in which autonomous vehicles can actually help better connect between different modes of transportation, but there are basically huge implications for the transportation sector and, as a result, climate change, depending on how we actually have these applications go forward. AI and machine learning are also being used for things like personalized advertising and on-demand delivery that are increasing how much we consume as a society, not always in ways that make us happier, but definitely in ways that increase consumption and emissions. AI plays a big role in how we consume information online. In some ways, it can contribute to misinformation and polarization by kind of spreading more incendiary content because algorithms are optimized to incentivize clicks, which, more provocative content is more clickable. It can also be used, though, to help us detect misinformation or to serve better climate information. And so kind of there's almost this battle being fought about how AI is being leveraged to serve information, and this has huge implications for climate action as well. And then AI today is being disproportionately kind of driven and developed by kind of a small set of companies that have access to large amounts of compute, that have the ability to store large amounts of data. And this creates various quote unquote power shifts in the sense of who actually is able to drive these technologies, who's able to access them, who's able to shape them. And that has implications for how we address climate change because it has implications for who actually holds the baton in terms of making decisions in the room. And so it's super important that we're cognizant of this as well. So what can we do about this? I want to address kind of two major audiences here, which is researchers and practitioners, as well as the climate and policy communities. So for researchers and practitioners, one thing that we can do is really make sure that the way we develop AI is serving the needs of climate change related applications. I talked earlier about how a diverse set of settings like those that appear in climate change require diverse approaches. And that means that there are lots of different ways in which we should be innovating that are driven by the needs of climate change applications. And we shouldn't be buying into narratives that developing one specific type of AI that is owned by one specific set of companies is going to be the way to address climate change using AI. It's not, and we need to fund innovation from across many different organizations in many different ways. Another is to kind of, choose what to work on. Ideally, work on climate relevant applications and don't work on kind of applications that clearly counter climate goals. And while it seems funny, there are tech companies who have explicit programs that are explicitly marketing to give business to, for example, the oil and gas sector. So it's something that we really need to do. But there are also more subtle things. For example, if you're working on something like autonomous vehicles, you can choose whether you're developing methods that are going to more likely get us to public and multimodal transit or ones that will entrench the role of private transit. Or a couple of other examples, which is for on-demand delivery. You can try to do things like actually build fuel efficiency and energy efficiency into the objective functions that your models are trained on, and a bunch of other things like that. Really think about, for this specific application, what would cause it to become climate aligned or not, and how can I actually change my technical approach and the organizational approach around it to do that. And then in terms of this idea of who kind of owns or is able to shape AI for climate applications, it's important to adopt an equity-focused lens, which means things like asking questions like, who am I working with? Whose problems am I centering? Am I kind of creating chatbots based on what will make the most profit for a particular set of companies, or am I actually helping smallholder farmers address issues associated with climate-related drought? And then when I'm doing that, am I kind of creating technologies in a way that I'm shipping them off to other people, or am I helping to build capacity and understanding and ownership among the people that I'm working with? There are different ways to do this with respect to training, with respect to transfer of money, and so forth. There are also lots of practices organizations can take, like adopting internal carbon prices in order to drive better behavior. And I think it's important that researchers and practitioners are actually really cognizant of the way that they communicate publicly about AI and machine learning. There are a lot of people, especially in the climate sphere, who are desperate and who are looking for solutions. And if we oversell the efficacy of our technologies, if we kind of brush the risks under the rug, this doesn't help anybody because it can cause AI to become a distraction and to not be used where it's actually most well suited. So kind of publicly communicating appropriately about the opportunities and risks so that everybody can go in with clear eyes and a clear head is really important. For the policy community, I think there are lots of different ways that policymakers can help to foster the use of AI for climate action in ways that are really aligned with where we need to get, as well as to reduce the negative effects of these technologies. So things like establishing data task forces in climate-related sectors, making sure funding is impact-driven, kind of ensuring that there are incentives to actually kind of engage in participatory design with stakeholders, large-scale education programs, as well as things like making sure that AI strategies, like governmental AI strategies, are actually building in climate-related assessment. So every AI application that is kind of, for example, procured by the government needs to go through assessment of what its emissions impacts are related to its compute and hardware, as well as the emissions of its applications, and then kind of promoting more transparency from data center providers, from tech companies on what the emissions impacts of these technologies are, so that we have better estimates that we're actually able to act on and inform policy around. So for those who are interested in kind of engaging more in this area, I would definitely encourage you to check out the climate change AI community. We have various summer schools where you can kind of meet others and learn more about the space, workshop programs where you can share work, funding programs where people can get resources for their work. And just it's generally like a really great community of people who really care about these issues and are really excited to think more about what it means to align AI with climate action. So with that, thanks so much. I know I'm over, but I hope we still have some time for questions. And again, thank you.
Okay, I'm going to start with, oh, is this on? Yeah. I'm going to start with a question from Slido, and you all can be thinking about any questions that you might have to come up here next. So, because the climate change that's occurring now is sort of unprecedented, how can AI be useful for projecting the future climate change, kind of like your COVID example? It couldn't kind of figure that out. Climate change is kind of similar. So how can AI be used to help figure out what's going to happen in the future?
Yeah, that's a great question. And this idea is that because the climate is changing, it means that data now is going to encode different patterns than kind of what's going to happen in the future. And so where I think some of the most promising examples are of AI being used to help improve climate projections is actually to supplement existing climate models. So climate models will actually write down the physics and actually try to solve over them to figure out what's going to happen in the future. And that can accommodate things like the actual on-the-ground situation changing and the physical processes as a result running out differently. But what happens is that the climate models are really expensive to run. And so what you try to do is you use machine learning to approximate portions of the physics, which I talked about, in order to allow the overall physics model to run faster. And it's still physics under the hood, so it can deal with the fact that the climate is changing, but you're just allowing the model to run a bit faster. Another area that's really cool is called climate and weather downscaling. The idea being that you have a climate model, it will predict what will happen in the future, but in a really coarse-grained way. So again, this example of kind of 1 or 2 predictions for the entirety of the state of Washington is not actually kind of exaggerated. That's sometimes the resolution at which a climate model might give you an answer. And so what people do is they say, well, if I want to know what the weather is in a particular place, I actually have a lot of weather data that's very fine-grained. And if I run my climate model backwards and ask what it would have told me the climate was in the past, I can get basically this data set of my past really fine-grained weather data and my past really coarse-grained climate model output, and I can learn the relationship between those two things. And so that way, when I have a climate model output in the future, I can apply that learned relationship to the future and try to figure out now what would the weather be in a more fine-grained way in the future. So there's some ways that basically machine learning can help process the outputs of climate models and learn the relationship between climate and weather data in a way that allows more fine-grained predictions.
Thank you, Priya. I'm just here to encourage you. If you have questions, we have time for a couple more, and we'll turn it over to this person here and invite you to come up if you have questions as well. We'll be alternating Slido and in person.
Thank you for the very informative talk. I was wondering, could you share some examples of more efficient ways? You mentioned about some incentives that machine learning programs would have an incentive to be more efficient so as to reduce the computing needs so that the same work gets done, but there are fewer climate emissions.
Yeah, and there are actually 2 things I would say that are captured in your question. So what are some technical approaches to reduce emissions, and then what actually causes people to actually use those? So the first, so in terms of technical approaches, there are approaches like model pruning that allow you to do things like, if you have a bigger model, you can actually kind of construct a smaller model that has the exact same parameters by basically, or that has the exact same performance by basically learning how to intelligently cut out individual parts of the model. There's also a kind of area called AutoML, which is basically a way to automatically try to figure out how to best construct your machine learning model. And sometimes that can be worthwhile in the sense that you might try out a bunch of machine learning models up front, and that process of trying out a bunch of different machine learning models may be more kind of energy consumptive than if you hadn't done that. But by doing that, you can converge on a model that is smaller, so that when you use it a bunch of times, the kind of use phase is less emissions consumptive, and so the overall emissions from that go down. So those are a couple of strategies. There are also some kind of innovative hardware strategies like capping the maximum power on your GPU, your graphical processing unit, to 80%. And that apparently doesn't really impact the training or use of the model, but actually reduces its energy consumption by quite a lot. So there are a lot of technical strategies. in terms of incentives, on the one hand, all of these things kind of by bringing down energy usage, bring down costs. And so some people will tell you, yeah, we're very incentivized to do that. But in reality, what a lot of entities are looking at is it worth this energy consumption because it will help me make more of a profit if I use a better model? And profit is not what the world is optimizing for. Emissions is what the world is optimizing for. And so I think there's some macro level incentives, things like carbon caps, carbon prices, things like your standard climate policy instruments that can help incentivize or enforce that entities have to care about their emissions.
Okay, we'll do another one from Slido. So thank you for mentioning the massive power shift to the small group who control AI. In what ways have you seen people organizing to democratize this resource?
Yeah, so I think there are a couple of ways. So one is specific philanthropic or governmental funding programs that are explicitly trying to fund academic institutions, nonprofits, and so forth to be the owners or developers or shapers of AI and machine learning. So Climate Change AI, we provide grants to organizations, to academic organizations to develop AI for climate change, but they have to do it in collaboration with a nonprofit or a governmental entity or a startup or somebody who would actually go on to use that technology. And those organizations need to be involved from the get-go so that they're shaping and owning those technologies as well. So there's some programs like that. And then I think just like large-scale educational programs play a huge role here to make sure that more people are able to shape these technologies. Mozilla also recently announced their kind of public AI strategy, which aims to kind of build kind of open source and kind of publicly maintained AI infrastructure that is kind of parallel to closed source and private infrastructure. And then there are portals like Hugging Face that actually try to replicate some of the most kind of high-performing AI models in an open source way. So I think there are a lot of initiatives that are really trying to shift the balance of who owns and shapes these technologies, but there needs to be a lot more.
Hi, Priya. Thanks for the really interesting presentation. Again, focusing on the energy emissions, and I just wanted a broader thought. We went into a lot of detail, but a broader thought. The estimates are, and I just did a quick look up, that energy consumption will go up 20% by 2030. In one sense, it seems like the reasoning is circular. We need to build AI, which is going to increase global emissions, to build an AI that can help us reduce global emissions. And just broadly speaking, in the academic community, which we come from, does that thinking make sense, or does anybody actually talk about that?
Yeah, it's a great question. And I think that one thing to kind of also recognize is that like the academic community is not homogeneous. So not all groups of people are driven by the same goals, which is to say that the types of AI and machine learning that are potentially driving that increase are specifically kind of foundation models, large language models, generative modeling, and so forth, often not the same types of techniques that people who are kind of leveraging AI for climate action are using, where those models might be more physically informed, which often means less data, which often means less compute, and so forth. And so there are these competing thrusts in some sense within the AI community. And there is some, I think, disingenuous discourse that is going on around we should continue kind of developing generative AI models and kind of building data centers because it's going to be helpful for climate. But it basically conflates generative AI with AI as a whole in a way that is convenient, because it can be great greenwashing to say, you should fund us to develop this specific technology. It's going to be great, I promise. And sort of glossing over the fact that this particular type of AI, which happens to be very consumptive, may not actually be the one that is useful in addressing climate. So I think basically there are a lot of, nuances to that trade-off, but I would say people who are trying to make that direct comparison and try to claim that this particular growth will kind of fuel AI-related or climate-related applications are often greenwashing rather than addressing the nuance of the fact that we need to be actually fostering a variety of approaches, many of which are not energy consumptive, but are nonetheless useful. So that's only a partial answer to a very long question, but I realize we're kind of getting to, yeah.
And we're making Priya late for dinner, so please join me in thanking Dr. Priya Donti for her lecture tonight.